welcome to today's lecture. We are going to discuss lap formation as well as material flow regulation in blow room. So, we will first start with formation of lap. So, you can see the diagram on the right hand side. This is a cross sectional view of scatcher. Scatcher is the machine which actually makes the lap. At the bottom you can see a photograph of some laps. So, from the photograph itself we can say that the lap is basically a compressed sheet of cotton tufts rolled into a cylindrical form. So, it is the final package of the blow room machineries. So, after opening and cleaning, we produce a package and this package is lap. Now, you also know that sometimes the blow room is directly connected to a set of carding machines, and in that particular case there is no need to form a lap because the tufts are directly blown or taken away from the blow room line to the cards. But in some situations or in some cases we are still producing laps. So, therefore, we are going to study how this sheet of cotton is produced and then rolled into a lap. So, the part of the blow room that produces lap is known as scatcher, and as we can see that a scatcher consists of a Krasner beater here, then a cage with internal suction, a perforated cage with internal suction. Then we have a calendering section which is here. You see the calendar rollers, which are basically 4 steel rollers placed one on the top of the other, and there is lot of pressure which will be acting on these rollers. And then there is a lap formation unit which consists of shell rollers as you see it here. Then there is a lap spindle which is shown also, and there is a pressure applying device on the lap spindle which is not shown here, but there is a device by which we can also put pressure on the lap spindle, so that when the lap is produced it remains in a compact state. Okay, so, these are the various organs of the machines, and prior to this the Krasner beater, which is a very fine cleaning units, and it can only handle the very small size tufts. We have feed roller which is feeding the sheet to the Krasner beater section. Then behind that there is a pedal feed arrangement, it is here. So, that the tufts are, we will discuss about the pedal feed arrangement. So, the tufts are made to pass between the pedals and the pedal rollers which is here, but before that there is a feed lattice and there is a reserve box. The reserve box is basically a box in which there is a column of tufts which is ready for being processed by the Krasner beater. We will now discuss the working principle of this scatcher unit. The tufts are stored in the reserve box to ensure a steady supply of material to the scatcher. The scatcher will work continuously, so you have to ensure that there is a steady supply of material, and therefore the reserve box is there where we store the material and keep it ready for being delivered to the Kirschner beating unit, or you can say cleaning unit. The feed arrangement to the Kirschner consists of pedals. So, you can see the diagram here, the pedal is here and there are 18 pedal levers. So, you can see this looks like a lever, and on the lever there is a long tail which is also visible here. This is long tail of the lever, and we have actually 18 pedal levers placed one after the other across the width of the machine. Besides, we have a pedal roller and a pair of feed roller in front of it. So, this is the feed arrangement to the Kirschner beater. Now, why do we have this kind of arrangement? On the right hand side of this slide, what you see here is a cross sectional view of the pedal roller and the pedals. So, you see here that there are 1, 2, 3, 4, 5, 6 up to 18 pedals. They are basically pedal levers, they are placed one after the other and they can work independently. And the green rectangle that you see is basically indicating the material which is there, and on the top of it we have the pedal roller which is fixed. So, pedals are there, the material is there and the pedal roller is there. So, the other end of the pedals are basically having some dead weight or some other weight because of links which are there. I will discuss about them. The pedals will always, the two ends of the pedals, one is the tail part of the pedal and the other one is the nose part of the pedal. So, if I simply draw the diagram of the pedal, let us at the bottom of this. So, it is like something like this. It is centered over here, here is the pedal and here is the pedal roller is there. Okay. So, therefore, the material is here. So, because there is a weight or of the weight is acting on the other end of the pedal, and therefore, this side the nose part, this is called the nose part of the pedal and this is the tail end of the pedal. So, because of this weight which is here on the tail end, the nose end will try to move up and it will try to compress the sheet of cotton or the fiber whichever is here, that will be pressed. So, the material is made to pass in between the nose part of the pedal and the pedal roller, and the nose part is as a force which is acting upwards, and hence it is trying to compress the tufts which are there. This is what is how the pedals will be working. Now, in the next diagram if you look at it, you see that the green part is of different thickness. So, let us say that the sheet which is being fed or the mat of fibers which is being fed, they are not of uniform thickness across the width of the machine. In that case, what is going to happen? The pedals will be somewhere compressed, somewhere they will be, pedals will be always compressing the material. So, depending upon the thickness of the material, the pedals will move up or move down from their nominal position. So, when the sheet thickness is more or less uniform or the thickness of the mat is nominal, then there is certain locations, let us say that location is here. Now, from that location the individual petals will move up or down depending upon what is the mass of material in between the pedal nose and the pedal roller. And what we see here, that some of these, like this pedal nose has moved down from its nominal position, this pedal has moved up, this has moved up. So, it all depends what is the mass of material in between the nose of the individual pedals and the pedal roller. So, they will move up and down, and what is the resultant of this? We will discuss that. Because of the pedal arrangement, one advantage that we get, the material is gripped firmly at each locations. So, if you have 18 pedals, so the material is gripped at 18 different locations, and at each and every location it is gripped with a force which is quite strong. Otherwise, what will happen, that if there is a variation in thickness in the material being fed across the width of the machine, and if we have a single plate, I think we have discussed it earlier, then the thicker portion will be gripped much more firmly than the thinner portion. But if we have a set of pedals, then this can be avoided. This was discussed earlier also. So, material is gripped at each location firmly, and the tufts, then what happens? This is being fed to the Kirschner beater. Kirschner beater is trying to open out the tufts further, and after opening them out, whatever trash has to be extracted, they get extracted, because below the Kirschner beater chamber we have a set of grit bars that we have seen in other machine earlier also we have discussed. So, some trash particles will fall down, but most of the tufts now will be flown forwards, and they will be deposited on the perforated cage. So, the material will go from the Kirschner beater to the perforated cage. So, this is a cage where there is an internal suction. The cage is connected, this perforated cage is connected to a suction fan. That means, through this perforation we are sucking air, and that air current will carry the fibers from the chamber, beater chamber, onto the surface of the cage. So, all these tiny tufts will be deposited on the surface of the cage, and the cage actually rotates slowly. So, there will be thick deposition of fibers in the form of a mat, and this mat will move forward. So, as it moves forward, by the time it comes to the other side of the cage, it is already in the form of a thick mat or thick sheet. Now, this sheet is made to pass or delivered by a pair of rollers, and from there the sheet will be passed in between the nibs of the calendar rollers. So, how many calendar rollers we have? We have 1, 2, 3, 4. So, this is the entry point of the thick mat or sheet, and then it is taking a path as shown in the diagram. So, and the calendar rollers are under heavy pressures, and how much pressure? The maximum pressure we can adjust to the extent of 6000 kg force. So, this force is acting on the sheet of material now, because we want to compress the sheet. So, once it is compressed, the sheet has got certain amount of structural rigidity, that is, they have got some amount of minimum amount of strength, so that we can really now roll them in the form of a lap. Now, the sheet is going as it is shown in the diagram, and then you see there are two rollers called shell rollers, they are rotating, and the lap spindle as shown in the diagram is resting on them, and the lap sheet is actually comes into contact with the lap spindle and it starts getting wound around the lap spindle. So, the lap spindle gets its drive from the shell rollers, and the shell rollers are turning at a constant speed, and therefore, the lap also moves at a constant rate, in the sense that the rotational speed of the lap will change and the diameter of the lap will increase, but the circumferential speed of the lap will remain constant, because the drive is friction drive from the shell rollers, and hence the sheet of lap here is not going to break. Otherwise, if we try to rotate the lap spindle at a certain speed, then as the lap grows in diameter, the surface speed of the lap is going to increase and there will be a stretch, and because the feed from the calendar roller side is constant, but the take up by the lap spindle is going to be more and more, and hence the lap is going to break. So, to avoid that, we do not give positive drive to the lap spindle, and we make sure that the spindle or the sheet of cotton around the spindle gets its drive from the shell rollers. So, when the sheet is wound around the lap spindle, now we also try to impose some pressure on the lap, so that the lap does not become too bulky. So, lap tube is pressed against the lap rollers and the pressure on the lap tube is generated pneumatically to the tune of 1000 kg force. At such a heavy force, we are trying to wind the lap sheet. The lap diameter could be to the order of 550 millimeter. So, it can go up to 55 centimeter or so, or it could be less than that. We can adjust the diameter of the lap. The weight of the lap can be made today to the extent of almost 40 kg. So, we can have lap maximum up to 40 kg, it can be also less than this. So, some technical parameter about lap. The lap length is usually around 40 meter. Delivery speed, that is the surface speed of the shell rollers, or you can say the calendar rollers, is around 8.5 meters per minute. The lap hank in any is 0.0013 to 0.0017. The lap weight per meter could be 350 to 450 gram per meter, that can be adjusted, and the production rate typically can vary from 1200 kg per 8 hour to 1600 kg per 8 hour. This is a typical productivity, or it could be more, a little bit more also. So, this is how the lap is formed. Okay. Now, we will show you a video. Just wait, we will just, you will see how a lap is actually getting formed. So, we see the lap is being delivered by the calendar rollers here, and you see it is moving out from the calendar rollers, and you see the shell roller over here. The sheet is being wound around the lap spindle. The lap spindle is this steel colored spindle, which is visible here also. So, we are forming the lap. Okay. So, that is about the formation of the lap. Now, we move on to this part the next part of the lecture, that is material flow regulation in blow room. So, you have seen that in the blow room the equipments are many and they are all connected together or linked together in series. So, we have bale breaker or bale openers to start with, then we have coarse cleaners, then we have a mixing equipments, and then you have fine cleaners, or you can say the intensive cleaning units, and after that either we have a lap formation unit or we directly deliver the clean tops to the carding machines. Now, the blow room line being quite long and there are so many machines which are connected together. So, there is a storage unit within the line to ensure steady supply of material to the downstream units. It is important to ensure the material flow between these interlinked equipments remain steady and they remain balanced, so that a situation does not arise when some equipments are not running because of want of material. We have to ensure that there is a flow of material through the entire line and the machines are working most of the time, they are not idle, and for that the material flow needs to be properly regulated. So, type of control or regulation which is practiced in the blow room line could be two types. One is on off type of regulation and the other one is continuous type of regulations. On off type of regulation we have on bale opener or hopper feeders, or also we have filling chutes. In one case, in the bale opener or hopper feeders we have sensing levers, we will discuss about them, and in the filling chutes or reserve box we have optical sensors, but these are working on the basis of on off principle. And also we have continuous regulations, and that is there in the Scotcher, and the example is the piano feed regulation that we have discussed just now, but we will be discussing now in little bit more details about the piano feed regulation. So, there are two types of regulation, on off type and the continuous type. First we will discuss about on off regulations. So, on the right hand side we see it is a sketch of a bale opener or hopper feeder, whatever you say, this typical looks like this. The red line that you see here, this is basically what? Now, this is basically sensing lever. So, the purpose is to maintain. So, we have a sensing lever over here within the bale breaker or hopper feeder, and the purpose is to maintain the volume of material within the hopper constant, so that the delivery from the feeder remains also fairly constant. If we can keep the material volume within this bin constant, then the delivery from here also will be constant. So, to keep the delivery constant, we have to maintain the volume of material within the hopper fairly constant. The hopper in turn receive material from the feed lattice, and the feed lattice we are dumping material, and that is what is highly variable in nature. So, the idea is that through this system of control we want to have, we have to make sure the delivery from the machine is fairly constant when the input to the machine is quite variable. Let us say the target volume of tuft within this hopper feeder is V t, that is the target. So, generally what we want that this V t will be 3/4 of V, that is whatever is the overall volume of this hopper or the bean here, 3/4 of this should be filled with material always. So, that is our target. So, V t is therefore 3/4 V, where V is the total volume of the hopper bean. So, how does it work? We are going to discuss this. Okay, before that let me just discuss a bit about the sensing lever. The sensing lever is a lever which is hanging here, the red line is showing it, and when the material with the within this bean increases in volume, this sensing lever is going to be pressed and it will move on the left hand side, it will swing backwards. So, the more material is there, the more will be the swing in the backward directions, and when the swing is around 45 degree, it reaches its maximum limit, it comes into contact with a sensor, and that sensor is then going to stop the machine which is feeding material to the hopper feeder. In this case, what is feeding material to the hopper feeder? It is the feed lasses. So, when the swing is maximum, the drive to the feed lasses will be stopped, so that nothing gets fed to the hopper feeder or to the bell opener, whatever it is. Okay. So, to start with, let the hopper feeder be 1/4 filled. So, there is not much material. Our target is we have to go to the level of V t. The sensing levers remains vertical, and in this case it will allow the feed lattice to run at full speed, and therefore, the material will be delivered from the feed lattice to the hopper. It will keep on receiving material and feed lattice will keep on delivering material. As soon as the volume of top within the bean is reaching the target volume, and what is the target volume? It is 3/4 of total volume, that is 3/4 V. So, by the time V top is equal to V t, the lever will swing upwards to the fullest extent, that is 45 degree, and presses a switch and stops flow of current to a motor which is driving the feed lattice. As a result, the delivery to the hopper is going to be stopped. Now, as soon as it happens, but the system has certain inertia. Due to inertia of the system, that is the motor pulley, the lattice, the feed lattice will continue to move for some more time and deliver material into the hopper. By the time I press the switch, delivery is not stopped immediately, because there was some inertia of the feed lattice which was moving earlier. So, it will still continue to deliver some material within the hopper feeder. So, this is what is now on the right hand side, you see a diagram. This diagram is showing how the volume of the hopper feeder, the fractional volume occupied by the tufts within the hopper feeder is changing with time. So, what we see a kind of sinusoidal a curve. I will explain to the curve. Now, let us say initially we started at where it was not at all filled, 1/4 volume was filled. So, with time the hopper feeder keeps on receiving material from the feed lattice. So, what happens? The volume of top keeps on increasing. So, it is going up and up and up, and it reaches the target value V t. This time the lever has sensed and it has sending a signal to stop the feed lattice. but as I said, because the feed lattice has got certain inertia, it will continue to feed for few more seconds, and therefore, the top volume within the hopper feeder is going to rise, and it will reach a peak maybe 0.9 V or maybe whatever little more is more than Vt, whatever is the target volume, it will be maybe 20% more or 30% more, it will reach some volume. But now what has happened? The feed is going to be stopped, but the material collected within the bin or within the hopper is little more than the target value, which is Vt. Okay. Now, the supply has stopped, but the inclined spike lattice will continue to now deliver the material from the machine. So, from one side we are feeding, and from the other side there is a delivery also, because the spike lattice is moving and delivering the material which is there within the bin. So, the material volume after reaching the peak will move down and down. So, it is going down and down. So, volume is going to reduce, and a time is going to come, by the time it is going to close to the target, and it will go below the target value of volume. Now, again the swing door, that lever is going to act. The lever will act again, and it will send a signal, and as a result the motor is going to start, the feed lattice is going to start, and it will start feeding material inside the bin. So, here also because of inertia, now the spike lattice is delivering material, and by the time the sensor is going to sense the material and send a signal, some more material will be removed from the bin. So, therefore, the volume of material or volume of top within the bin is going to decline from the target value to some extent, and by the time the feed lattice starts its movement, the volume of top within the bin keeps rising again. So, what we see here now, that before the supply resumes, the volume will continue to fall to a level of almost 0.6 or 6 by 10th, and thereafter it start rising again. This type of control will cause the volume of material in the hopper to vary in a cyclic manner between 0.6 V to 0.9 V. That will be a typical kind of variation which will be there. So, it will move in a cyclic manner, even though target is Vt, sometimes it will overshoot Vt and sometimes a little less than Vt, and this kind of movement or change in the volume of material within the bin will be there. So, it will never be exactly Vt, that is the 3/4 V that we want, but sometimes a little more, sometimes a little less. That is how it is going to be there. So, on off control will give you a control which is changing little bit from the target value. Sometimes it will be little more, sometimes it will be less. Now, the result box that we see in some of these hopper feeders or some other machines, they also work on the principle of on off control, or you can say sometimes we call it stop go control also. So, in a reserve box on a filling chute, what we do, we have to maintain a correct height of material in the chute, that is our objective, and what we have an optical device. There is a light source on the left hand side and there is a photo cell on the right hand side. This is how we placed a light source and the photo cell, and the light will always fall on the photocell unless it is obstructed by the column of material which is building up within the reserve box. When the height of the material goes beyond the photocell, the light rays are obstructed obviously, and that gives a signal that it is completely full. Obviously, the delivery to the reserve box is going to stop. So, normally one can expect a delay of 2 to 3.5 seconds between the sensing of the height and actually stopping the delivery. So, here also when it will stop when by the time this material height is going to be somewhere here, the light will stop and delivery of tufts within this box is going to end. And as soon as the reserve box is delivering material also to the next machine, and by the time the delivery will be such that the filling height has gone down and the light is falling on the photocell, the delivery to the reserve box will resume. This is how the on off control in the filling chute is going to work. Now, advantage of this on off control, the beating elements in the cleaning units run at the same speed always, or the constant speed basically. Once we set the speed of the cleaner, the beating element of the cleaner, it runs at the same speed. If it is 800 rpm, it will run at 800 rpm continuously. But delivery from the feeder remains intermittent. It is fairly constant over the time when it runs and becomes nil when it stops. What happens that these opening and cleaning units, though the beating element is continuously running, but the feed and delivery is sometimes stopping and sometimes resuming. Like whenever there is a need of material to the subsequent machine, there will be feeding to a particular cleaning unit also, and as soon as the feeding starts, the delivery also will be there. So, the delivery from the feeder remains intermittent, that is sometimes there will be delivery, sometimes there will be a stoppage, because the next machine may not need sometimes material, because there is a stock of material maybe in the reserve box or in the feeding chute of that particular machine. So, if we have sufficient material available in a filling chute, then the previous machine will be stopped, in the sense that the machine, if it is a beater or cleaning unit, the opening device will work, but the feeding to the unit will stop. So, as a result what happens is that there will be sometimes a delivery which is constant to the machine from the previous reserve box or some other, suppose the reserve box is there attached to a particular beater, then from the reserve box delivery is constant for a certain period of time, and then there is a time when there is no delivery. So, like here there is no delivery or there is a pause. So, to any opening or cleaning unit, what will happen that sometimes there will be delivery of material within the machine and sometimes there will be a complete pause. So, as a result of this, what is happening? The material will always receive the same treatment, because the speed of the opening element is constant, does not change, and if the delivery remains constant over a certain period of time, then this is the delivery time to the machine or feeding time to the machine, we can say. Then the machine is going to receive the material is going to receive the same kind of treatment. But the instantaneous processing rate is always higher, and this reduces the cleaning or opening ability. So, if you have a pause and a delivery, then on an average maybe the delivery is this much as shown by the red line now, but instantaneous delivery being sometimes more and sometimes 0, the cleaning and the opening capability of the machine is going to reduce, since I am feeding too much of material over a maybe over a certain period of time, and then for some period of time, even though the beater is running, it is idle, because it is not receiving any material within the chamber, and therefore, it is not really opening and cleaning the tufts. So, as long as I am not feeding any material to the particular opening and cleaning unit, even though the beater runs, it is not processing the material. So, when it runs, I am feeding more material, and sometimes I am not feeding any material. So, even though for a given average value, what we see that the instantaneous processing rate is very high, and therefore, it will reduce the cleaning and opening capability, or the full potential of opening and cleaning capability of the machine is not going to be utilized. Now, we will discuss the continuous regulation. So, that is all about the on off regulation, the other one is continuous regulation. We have already discussed a bit of it, that is pedals and pedal roller that we have. Now, we have earlier discussed that the nose of the pedals, they move up and down depending upon the mass of material which is there in between the pedal and the pedal rollers. So, these movements are then transformed. In what way? We will discuss this. The feed to the scratcher is regulated by the variable speed drive, which consists of cone drums. Now, you see there are two drums, these are known as these two are cone drums, there is a driver drum and there is a driven drum, and driven drum there is a set of gears which is driving a feed roller pair, and before that we have a pedal roller and the pedal with a nose here, and here is the fulcrum. Now, the pedal ends are these pedal ends are, so the pedal ends are connected by some mechanisms, and it is finally connected. The movement of the pedal ends is actually translated, and it reaches the cone belt which is driving the cone drums. Now, the belt position of the cone drum is regulated by the thickness change in the material detected by the pedal noses. So, here is the pedal nose, or you can say these are the pedal nose. Green part is the thickness of the material, mass of material. So, pedals are moving up and down. Each pedal acts as a lever, and the movement of the pedal noses are amplified by the lever arm. So, pedal tail ends will move much more than the pedal nose ends, because basically it is the lever. We know the lever ratio. If we find out, we can calculate that if there is a movement of 1 millimeter at the pedal nose, what is the movement will be at the tail end, and all depends upon the lever ratio. The tail ends are now connected by links, and the resultant movement is transmitted to the belt. So, there are from all these ends are connected by a set of links, mechanical links, and the net or resultant movement of that link is actually transmitted to the cone belt. For normal thickness or nominal thickness of the material passing under the pedal, the belt should stay at the middle. This belt location is should be at the middle when the nominal thickness of material is passing. So, that is the ideal location of the belt. As the belt is shifted, so depending upon the overall change in thickness across the entire width of the machine, the belt may be shifted from its nominal position, and if it shifts, the speed of the feed roller is changed and the feed is adapted to the change in thickness of material. That means, we are sensing the material here in the nose point, here we are sensing it, but we are controlling the speed of the feed rollers, which are these two rollers placed in front of it. Why we do so? Because by the time I sense the thickness of the feed and we take corrective action, because there is inertia of the entire mechanical system, the material will already move forward, because the material is moving continuously. So, the part which is sensed, by that time we take action on it, the material has already moved forward by few inches, and therefore, feed rollers are placed little ahead of the pedal rollers, and we take corrective actions on the feed roller, hoping that the material will reach the feed roller nip and we change the speed of feed roller. So, we sense at the pedal roller, but actually change the speed of feed roller. Thickness change is positive, that is, thickness has increased with respect to the nominal, the belt will shift to the right hand side and the speed of the driven cone drum will reduce, and when it is negative, the opposite effect is going to happen. So, depending upon whether the overall thickness has changed on the positive side or on the negative side, the belt will move either on the right hand side or left hand side from the nominal position, and accordingly the speed of the driven cone drum is going to change, and driven cone drum is feeding or driving the feed roller. These feed rollers are basically delivering material to the Kirschner beater. So, therefore, we will ensure that there is a constant amount of feed to the Kirschner beater in terms of mass being fed per unit time. Now, relation between the thickness and the drum diameters. To feed constant amount of cotton Q, the speed of the feed roller N must be inversely proportional to the average thickness of the material, which is T. Let us average thickness is T. So, Q will be proportional to pi d n into T, where d is the diameter of the feed roller and n is the speed of the feed roller. So, Q is proportional to this, and therefore, for constant Q, n is going to be proportional to Q by T. Okay. Speed of the feed roller n is directly proportional to the driven cone drum speed, that is, see, this is the driven cone drum, speed is n v, and through some maybe some gear ratios, it is feeding the drive to the feed roller. So, speed of the feed roller, which is n, has a direct relation with the speed of the driven cone drum, that is n v. So, n is proportional to n v, and therefore, n v is proportional to what? d r by d v into n r. what is, let us see here, how NV is connected to, see whatever is the speed of cone, the driver cone drum, which is NR, this multiplied by dr by dV is going to be the speed NV. So, NV is this as shown here, all right. Therefore, we can write that N is proportional to R. So, NV is R into NR, or the what is NR? NR is the, this will be capital R, NR is the speed of the driver cone drum. So, NV is R into small nr, and N is proportional to NV. Therefore, what happens? N is proportional to R. So, combining equation 2 and 4, we can say R is proportional to 1 upon T, or RT is equal to constant, that is K. So, R into T, therefore, the ratio of the diameters of the two cone drum and the thickness of the material, or the multiplication of these two is going to be constant. Okay. Now, let us say we will solve a numerical now based on this. So, the nominal thickness of material under the pedal rollers is 12 millimeter. At this thickness, the diameters of the driver and the driven cone drums are 250 and 200 millimeter respectively. What will be the diameter ratio if the nominal thickness changes by plus minus 20%? So, existing diameter ratio is 250 by 200, that is 1.25. What is the value of RT? RT will be constant. So, R is 1.25 and K is how much? T is how much? T is 12 millimeter, we know. So, this is R, this is T, and hence RT is going to be, this constant K is going to be 15. What is the change in this thickness now? The thickness, the new thickness is 20% more. So, 12 into 1.2, it will be 14.4 mm. Therefore, the change ratio is going to be how much? K by T1. So, 15 by 14.4, which is going to be 1.04. So, the belt will be located at a place where the ratio of the cone drum's diameter will be 1.04. We will now do this calculation, production calculation of the machine, of the scratcher. Production is always delivery speed into duration, where the production is in terms of meter, if we think. What is the delivery speed in meters per minute multiplied by the duration over which we want to know the length being delivered. So, this is the formula for this, very simple, straightforward. If I want to know the production in kg, so much length I am delivering, and now we need to know if this is the length I delivered and what is the lap weight in gram per meter, and if I want the unit to be in kg, so I divide this by 1000, that will give me the production in kg. Only thing I need to put these values of delivery speed and duration, that is whether I want to find out the production in 1 hour or 2 hours or 8 hours, whatever it is. I need to know these unknown, 3 unknowns are there: delivery speed, duration and lap weight in terms of gram per meter. Now, if the lap hank is given in terms of kilotex, lap hank is basically means what? Lap linear density. Suppose that is given in kilotex. In that case, production in kg is going to be delivery speed into duration, lab linear density by 1000. If I want per 8 hour delivery speed, 8 hours means 8 into 60, that is duration is 480 minutes. Lab linear density in kilotex it is given by 1000. Kilotex basically means gram per meter. So, production in kg 8 hour, delivery speed into 480 to lab linear density, and if we want to include the efficiency of the machine, then I multiply it by the efficiency divided by 100, which could be 80% efficiency, 85% efficiency. We can calculate easily the production. And in the production we want to know when the lap hang is given is any, because generally practice in the industry is to express the lap hang in any, that is English count. In that case, production is going to be delivery speed in yards per minute, duration, lap weight in gram per yard. So, everything changes now from meters to yard per minute. Production in kg will be delivery speed into, sorry, here it will be again if it is the meters per minute it is okay, then I multiplied it by 1.09. So, this factor is coming because delivery speed multiplied by 1.09 will give me delivery speed in yards per minute. Then duration, whatever is the duration I want, and the lap weight in gram per yard with lap hang, this is connected by this. This will give me the lap weight in gram per yard, because 840 into lap hang whatever it is multiplied by these two, weight of that many yard is 453.6 gram, that is 1 pound, and therefore, weight per unit meter is going to be 453.6 by 840, and the lap hang multiple lap hang, and that I want to convert into kg, I divide by 1000. So, it becomes 453.6 by 840 divided by 1000. That will give me the actually your production in kg. Now, if I want for 8 hour, duration changes. So, I bring it 8 into 60, rest remains same, and that give you a figure of constant figure of 0.2825. So, production in 8 hour in terms of kg is going to be 0.2825 delivery speed meters per minute by lap hang in any. If I want to include efficiency, I multiply by the efficiency factor, that gives you the production. And there is one example about production calculation. Scotcher is producing a lap of 0.0012 hang, delivery speed is given, find out production per shift at 80% efficiency. I straight away use that formula and substitute the values. We get a figure 2001, you have to practice yourself, you can work it out. If it is 80% efficiency, this will give me the figure, and production in the lap hang is made of 10% finer, that means the hang is going to be 0.00132, either earlier it was 0.0012, now it is going to be 0.00132, this is going to be. So, the production is going to be this much, and here also this will be 80. So, 0.2825 10 by 0.00132 into 80 by 100, which will give you a figure 1819 kg, and then the loss in production will be difference between these two 182 kg, and therefore, loss in production in terms of percentage also we can find it out is going to be 9.1%, because the third part is the percentage loss in production due to making the lap hang finer. So, this is, you do the calculation yourself, you will be able to learn very fast, and with this we close this session. Thank you very much.